Hi everyone. This presentation is about AI planning using evolutionary computation. I'm Jan Semé, and this is an item for the Creative Challenge of the Coursera AI Planning course of February 2013. I'm going to start by saying a few words about myself. I'm a research engineer. I'm a specialist of evolutionary computation and over computational intelligence techniques such as machine learning. I just joined the optimization and AI planning team at Thales Research and Technology near Paris. As I said, I'm a newcomer to the team and I don't know much about AI planning yet, which is why this course came at just the right time for me. What I will show in this presentation is a brief introduction to genetic algorithms and evolutionary computation, what they are and why they're useful. And I'm going to try to give an outline of DAEx, our state-of-the-art evolutionary planner that was developed in my team. And then I'll give a quick example of application to a real-world case. Before I start, I would like to state that the main researchers behind the research I'm going to show later in this presentation are Johan Réau, Pierre Savéan, Marc Genauer, and Vincent Vidal. The research was conducted within a consortium made of three entities: Thales, a large international high-tech company specialized in aerospace engineering, defense, security, and ground transportation applications; INRIA, the French National Laboratory for Research in Computer Science; and ONERA, National Laboratory for Research in Aerospace Engineering. Let me start by defining what is optimization. The goal of optimization techniques is to have computers automatically search for the best possible solution or solutions to a particular engineering problem. In this context, an optimization problem is made of three main components: a fitness or objective function, which measures the quality of the solutions, which can be costs or delays, in which case we try to minimize, and which can be profits or vehicle flows, in which case we're trying to maximize. You also have degrees of freedom or variables, which is what you can modify or play with to reach your objective. And finally, you have constraints, which limits what you can do with the variables. For example, you may have in an industrial context a set of security regulations limiting the values you can input in your systems for the various parameter settings. Optimization is at the confluence of several scientific fields, mainly applied mathematics and computer science, with their various flavors, such as artificial intelligence or operations research. Methods can be deterministic, stochastic, approximate, or exact, and the most famous names you may have heard of are enumerative methods, linear programming, gradient descents, or metaheuristics. My team is more specialized in stochastic metaheuristics, which are often inspired from nature and biological processes. Again, the most famous names are simulated annealing, taboo search, and colony optimization, or what I'm going to talk about today, genetic and evolutionary algorithms. Their key advantages are often said to be their ability to tackle very large or ill-structured problems, which are typical of real-world applications. They need very little information, such as derivatives, and they're anytime algorithms, which means that you can get a solution, good as it is, at any time during the search, not having to wait until the end of the search process. They're highly modular, which means they can incorporate any time of constraint or expert-provided knowledge, and have also natural multi-objective capabilities, which is again very interesting in a real-world application context. They can also be easily distributed. I'm now going to proceed to a brief introduction of our technique of choice for today, genetic algorithms. They're inspired from natural evolution as it was described by Darwin. The core principle of natural evolution, the core principles, say that a population living in an environment with limited resources sees its best individuals, which means the most adapted to the environment, survive and therefore transmit their genetic traits of excellence to their offspring. On top of this, random variations allow for exploration of new possibilities. Computer scientists found these principles very interesting and applied them to the solving of engineering problems, saying that it was interesting to evolve a population of solutions instead of a single one, and that characteristics should be explicitly encoded for that purpose, as a binary string of parameter settings, for example. Random variations would be used then to explore and exploit good regions of the search space found so far. The main kind of variations for genetic algorithms are crossovers, which is the equivalent of sexual reproduction, where individuals recombine their genetic material to produce offspring inheriting from their characteristics, and mutations, which inject novelty and originality in the search process. These algorithms have been introduced in the 1960s and have known an increasing success in real-world applications over the last 20 years. This is an example of a very simple genetic algorithm based on a binary string representation. It is applied to a toy problem for illustration purposes, the 1max problem, which consists in maximizing the number of 1s in the binary string, here of length 8. So we have a population of size 4. You have here 4 individuals with their genetic material, 0s and 1s, and this initial population is randomly created, which means each value is randomly picked. The first individual had just 1, so it has a pretty low fitness value. The second individual has 4 1s, so does the third individual, and the last one has 5 1s. The next step is the parental selection, which is random but proportional to the fitness values, which means the higher the fitness, the more likely it is for the individual to get picked. In this example, B and D, this individual and this individual get picked for reproduction. That's the next step, crossover. We have a father, individual B, and a mother, individual D, which produce an offspring by a recombination of their genetic material. A random locus is picked here, and the offspring has part of its genetic material coming from its mother and part of its genetic material coming from its father. Here we can see that this individual was lucky because its fitness value is higher than both that of his father and that of his mother, because the individual inherited from both the excellence of the father, seen here on the left part of the chromosome, and the excellence of its mother, seen here on the right part of the chromosome. Then you have the random mutation step, which consists in randomly picking a locus in the chromosome, here for example, and flipping the value. As it's a random process, the fitness value doesn't always increase. As we can see here, it has gone down. This process is iterated. We produce 4 new individuals. That's the new population. That's the first generation, with fitness values that already have increased on average. Again, we enter the loop of selection, crossover, and mutation, which produces yet another generation, generation 2, in which the fitness values are again increased on average. And here we notice that the maximal possible value for the problem, 8, has been found for a particular individual. So we can stop the search. The algorithm has found a good solution, here the optimum, to the problem. There can be a number of overstopping criteria. We can have limited time for search. We can have reached a dead end or found the known optimum. This is the general outline for evolutionary algorithms, as illustrated by the simple example I just gave. there's an initialization step to create the first population, evaluation, variation, and selection steps to produce offspring and select parents for the next generation, and the stopping criterion, which says when the loop should stop and the best solution found so far be retrieved. That's the general principle of evolutionary algorithms. This is an example of a real-world application for evolutionary algorithm, research work that was published in 2006. The goal of the problem is to minimize accumulated delays for trains after a small perturbation, which means a train being delayed for a few minutes at a station. This is illustrated by the space-time diagram you see here, where it's pretty clear that train C, going from station I to station J, at this particular timestamp, will be disturbed if train C prime is delayed at station I, preventing train C to arrive at the station at the predicted timestamp. The degrees of freedom for this problem include the tracks that you can be on in the various portions of the network and the arrival and departure times at the particular stations. How the problem was solved using genetic evolutionary algorithm was by coupling evolutionary search in the space of permutations and the greedy scheduling heuristics. What this means is that we reconstructed the schedule after the perturbation by removing all the trains and inserting them back one after the other. And the optimization was playing on the order in which we did this reinsertion. This is similar to a planning problem because it tries to optimize what the operator is doing after the perturbation while reconstructing the schedule, the actions being the insertion of a train in the schedule being reconstructed. This is the evolutionary loop you've just seen. An individual, which you can see here is a permutations, which means a list, an ordered list of train identifiers, which is used by greedy scheduling heuristics to produce a schedule. And you have the usual selection, reproduction with mutation and crossover, and selection steps. The best individuals are kept for the next generation, and the process is iterated until a sufficient quality solution is found. The results are, in terms of delays, minimized over search time, and there was a comparison with another optimization technique, linear programming, supported there by CPLEX. What is at stake in operational terms here is that 1 minute of delay on the network costs about $1,000, and real-time response is needed to face the perturbation. The results showed that the evolutionary approach allowed for a much faster response than the traditional linear programming techniques. We can now move on to AI planning, which, as you know, is about finding a path in a state transition system, or a sequence of actions linking an initial state to a state satisfying a number of goal conditions. Real-world applications usually make use of the PDDL language, which defines the syntax to define objects, relationship states, and actions in the particular application domain. This language has been important to researchers because it allowed them to focus on search, heuristics, and algorithms, and have the liberty to produce domain-independent planners. There are several kinds of planning problems. One of them, which is the focus of our team, is temporal planning, in which each action has a duration and can be executed in parallel with other tasks, provided resource constraints are respected. And the fitness function is usually the make span, which means the difference between the end of the last action and the start of the first action in the plan. The planner that was developed in our team over the last few years is called DAEx. It stands for Divide and Evolve with an Embedded Planner X. It won the deterministic temporal satisficing track of the 7th International Planning Competition in 2011. It's based on the stochastic divide and conquer principle and can solve any problem expressed in PDDA. The core principle of the algorithm is state-based decomposition. It means, as illustrated by this figure here, that instead of trying to solve the planning problem directly, here going from A to B, we can introduce intermediate goals that allow for intermediate problems to appear and which can be solved more easily with an embedded planner. Our embedded planner is the one developed by Vincent Vidal at ONERA. It's called the ASP. It's lightweight and very fast to find the solutions to intermediate problems and belongs to the forward state-space heuristic search family. We make use of a number of heuristics within the algorithm, including the H1 heuristic to determine for each ground atom the earliest possible starting time, and of heuristics to discard pairs of mutually exclusive atoms in each intermediate goals. We conducted a number of experimentation on IPC benchmarks, including in problems in the classical planning category, in the cost-based category, and in temporal planning as well. Let me now describe the decomposition principle more precisely. What you can see here is a timeline that goes from an initial state to a state satisfying the goal conditions. The timeline has been discretized thanks to the H1 heuristic, which gives us the earliest dates at which the various atoms in the strips universe can occur in the plan. To construct our chromosome, which is our building block for the evolutionary search, we need intermediate goals. To construct those, we're going to randomly select a subset of the timestamps, here 2 of them, T4 and T6, and for each of those we're going to build an intermediate goal. To do so, we're going to select again randomly a number of atoms in the set of possible atoms for that timestamp, and we're going to do so while respecting the mutual exclusivity constraints. Having constructed thus the intermediate goals, we're going to run YASP, the embedded planner, to determine which actions with their preconditions and effects allow us to move us from one state with a set of atoms to the intermediate goals specified in terms of atoms that we've just constructed. And the compression of all those intermediate plans will constitute the final solution to the problem that can link the initial state to the goal state. We can now zoom out. You recognize the evolutionary loop I showed earlier with a population made of parents, offspring, constructed from crossovers and mutations. Everyone is evaluated and the subset is selected and put up against a stopping criterion. What is specific to the planning problem here is that the individuals or parents are actually decompositions of the form I just showed earlier. The variation operators are actually only mutations and consist in adding intermediate goals. You just saw an example with 2 intermediate goals, there could be 3, adding atoms in those intermediate goals or deleting goals or atoms. The evaluation step is extremely important. It consists in first compressing all the intermediate plans produced by the embedded planner, and that by evaluating the resulting plan, if the plan is feasible, which means that YASP or the embedded planner found solutions for all intermediate subproblems, then the evaluation is made in terms of solution quality, may-expand, for example. If the individual or decomposition is infeasible, then there's a gradient measuring feasibility, which is based on the number of intermediate problems that were solved from the initial state. The loop, as in any evolutionary algorithm, goes on and on and on until either the computation time budget is over, or sufficient quality in terms of and may-expand, for example, is reached. So that's the outline, the general outline of our evolutionary planner. Our planner was applied to a variety of real-world use cases, including this example, which for the sake of brevity I'm going to have to cover rather quickly. The use case is about reacting to a terrorist attack in a subway station within the context of an emergency response toolbox. The aim of the optimization algorithm here being to find the best possible plan to produce shorter transportation time, better dispatching, and more generally a good adaptability to a changing situation with respect to the emergency. For example, being able to produce good plans even though the traffic is heavily congested that time of the day. The object of the system is also to be able to conduct what-if analysis, which allows for a good proactive work on strategic resource configuration and also proper training of emergency response forces, firemen, police officers, and so on. The objects of the problem are the various resources at stake, and whose role is explained by experts, whose expertise we collected and formalized using PDDL. The main bottlenecks are traffic congestions and hospital capacities, and the agents are victims and the police units, vehicles and hospitals, the environment being an urban road network, and the tasks at end being victim extraction and protection, and move to secure zones. That's a snapshot of the actual toolbox, illustrating the geographic nature of the problem with the various hospitals on the various parts of the map, the location of the various police vehicles or firemen units. That's the plan being tested here, and here the solution plan found by the system, illustrating how the tasks are executed in parallel. To sum up, I gave an introduction to evolutionary algorithm and suggested they were well tailored for large and difficult problems typically found in the AI planning contexts. I demonstrated how our evolutionary planner, DAEx, worked based on the divide and evolve strategy, which works well for planning because it successfully reduces complexity by finding good intermediate steps to the final plan. I also gave an example of using that planner in a real-world case where it was used to produce good emergency response plans. That's all I had to say. Don't hesitate to contact me should you have any question or need for further information. Thank you.